Well, I'd like to reiterate the welcome for all of you. This workshop has really grown over the last 3 years, and it's turning into a really fun and interesting workshop. So those of you that are here for the first time, I think you're going to enjoy the talks and also the discussions that we have. So like Jacob, I want to help funding this workshop. And I thought as part of the panel that I would give a few slides just kind of on my personal perspective and a little bit about what DARPA is doing. Now, I'm an MTO at DARPA, which is the Microsystems Technology Office. So we're the gadget people. We build stuff. We build hardware and what have you. Although the programs that I'm looking to start tend to be a mixture of hardware and algorithms. There is another office at DARPA, BTO, Biological Technology Office. They're actively involved in the BRAIN project, and they also have a number of programs in trying to understand the data that they, both collecting data from living brains and understanding and interpreting that data. And then also the Defense Sciences Office, DSO, has been ran the Synapse program over the last few years, which is starting to wind down at this point. So my first, it was a very nice introduction on Moore's Law. We've been very dependent on Moore's Law over the last, actually if you start from the first microprocessor, it is about 40 years. It's also about 5 to 6 orders of magnitude improvement in performance, which is really amazing. And although we've seen this huge increase in performance, we have actually not as yet solved a lot of the hard problems of intelligent computation. And believe me, we have apps. Coming out of the DoD, I can tell you dozens of applications that are drowning in sensor data. They don't have the on-platform compute power because of power limitations. And they're not interpreting, they're not dealing with the data the way they should. We have a lot of problems in the DoD, which you've all heard about, of complex systems. The F-35 fighter has been continually delayed. Often, there are many complicating factors there, but often the complexity of the software is one of the items that's, one of the explanations that's given for the delay in the system. So we have very complicated systems that are getting harder and harder to use and harder to prove correct. And then cybersecurity is becoming a huge issue, and there's a lot of room there for applications as well. I'm not so much focused on medical. We do have medical applications in BTO, and they are looking at some possible ways that some of these networking and algorithmic ideas could apply to the things that they're doing. So we've had 5 to 6 orders of magnitude, and I contend that the primary reason that computers are as intelligent as they are today is mostly because of the 5 orders of magnitude. There's been some improvements in algorithms. I certainly don't want to diminish that. But we don't have 5 orders of magnitude left. As the previous speaker mentioned, power scaling has stopped, clock frequency has stopped. We can still put more transistors on a chip, but that's slowing down, and that will stop before too much longer. So we're kind of stuck. We've relied on this wonderful Moore's Law, and now we can't rely on it anymore, and the question is, where do we go from here? I personally believe, and I think a lot of you may agree, that biological computing is still the best, perhaps the only answer to how to leverage technology as we go forward. But the future is kind of not completely obvious yet. There are a lot of factors. For example, there are very few applications that have any major neural component to them. I think that's improving, but typically it's been a niche. It's held a niche in certain applications, and that obviously hasn't justified the hardware investments that we would like to see as well in the area. So the question is neural the solution? So one of the things I think as a community we need to do to the people who work outside this area, and it's one of the things that I'm certainly trying to do at DARPA, is we need to really articulate what exactly do these networks give us? What specific computations do they contribute? How are they going to play in the applications of the future? And I think we, as a field, we've been a little remiss in doing that. And personally, at DARPA, I cannot use the brain does it this way argument because we don't know how the brain does it. So the fact the brain does it doesn't help us much in trying to propose these networks moving forward. I also kind of, just to get on my soapbox a little, I think we need to be really careful with the hype. I think the field has a tendency to hype, and sometimes it's not the participants' fault. Sometimes the journalism community will tend to hype what we do. I'm pretty comfortable with the terminology we use, but we're really not solving applications yet. And I know there are a lot of people who say, hey, I've got these great applications. Oh, what are your applications? Well, I can do hidden Markov model. That's not an application. That's an algorithm. Okay, it's a small piece of a larger application. And I don't believe we're doing cognition. It's a great goal for us to have in the long run, but if you go back and look at the definition of cognition, we're a long ways from doing that. And I don't think we understand completely how real neural structures implement some of these characteristics. Also, we need a systems perspective. We've been focused on point solutions for a very long time, and there's been some very good results in those areas. But you all see the press. Somebody has invented a memristor synapse, and it's like, okay, that's it. Now we can build a brain. When in fact, that's just a small piece of a very large problem. So a systems perspective is absolutely essential, I think. There's been a lot of great progress. Most of you are aware of the deep learning results. There are many other benchmarks and results, but through the ImageNet application, where you have millions of images and thousands of categories to choose. And in 2012, there was one deep learning entry into the system, and it beat everything. And now that's all that's used in the ImageNet benchmark, or deep learning. However, they have their problems too. Some of you may be aware of this paper from Jeff Clune and his group, where he actually did a genetic algorithm. He took an image and he kept modifying the pixels in the image until he got the neural network to say, oh, this is this category, it's that category. The goal was not to be critical of the technique, but just to say it still has some limitations. Current machine learning is pretty good, but I think we still have challenges, and hopefully some of the things that we'll address in the next few days here. Learning is very compute intensive, typically done offline, so that rules out a lot of real-time learning applications, which many in the DoD require. Incrementally adding new information can be difficult with a lot of the algorithms. You have to retrain from the beginning. Temporal information tends not to be handled very easily. There's very few models that actually have feedback, which, as we all know, is extremely important in biological networks. And they tend to require very high precision, which sort of reduces any return on investment in specialized hardware. Doesn't eliminate it, but it makes it a little less, makes the ROI a little bit lower. And they typically, there's many learning algorithms are starting to add ways to sparsify the data, but for the most part, sparse representation, which I think is a key element of neural data representation, is really not visible in many of the algorithms. And this, to me, then, is a motivation for looking more to biology. By the way, just so you know, I use the term HTM, with courtesy Jeff Hawkins, from his book on intelligence, to really refer to more biological-like learning and intelligent computing algorithms, and to distinguish it from some of the other more traditional machine learning approaches. I think there are a lot of advantages in the biological space that we need to figure out how to pull into machine learning. One is fast learning. One-shot, or what David Mackay called one-and-a-half-shot learning, has a lot of promise. Self-organization into hierarchical structures with feed-forward and feedback control, and some models have lateral connectivity. Representation of temporal information efficiently. Efficient mapping to hardware, especially if you're dealing with modest to low precision, you can have some very high returns on specialized hardware. And scaling is a big issue, and the online learning and real-time learning allows us to scale. Anyhow, here we go again. We're having another resurgence. It feels right this time. Computational neuroscience is producing broad and deep models. We have machine learning being used in real applications. Moore's law has given us extremely powerful computing, allowing us to emulate large, both biorealistic as well as abstract models. And for the old-timers here, like me, we are now entering what I call the third age of neurocomputing. Hopefully this is it. And frankly, I don't think there are a lot of alternate paths. I think a lot of the traditional approaches are stuck. So the neuro has, I think, a lot of opportunity facing it. I'm taking a little longer than I thought, so I'm going to go fairly quickly. These are the kinds of things that I think the neural-inspired algorithms can give us. Fast learning is an important one, and I think, as I said earlier, a lot of application in DoD that really need fast learning. Ability to capture complex structure This is one of the things that traditional algorithms don't do well. And we really, as we move back into a system, we need to actually capture complex relationships between the data. Sometimes these are referred to as grammar, sometimes they're graphical-like structures. But I think that neural models have a great opportunity to provide ability to do some of these things. And I think some of the sensor architecture, many of you are aware of the work that's been done in the neuromorphic VLSI community. There's a lot of interesting work on various kinds of dynamic vision that the group at Zurich has done, I think, have a lot of potential in helping us out. And I personally think with specialized hardware, these new kinds of algorithms are going to revolutionize sensor data and control systems. This is an example of structured data, how the relationships of the components really form the object. But I'm going to skip over that. And I wanted to talk then about DARPA is actually considering a possible program called the Cortical Processor. The objectives of the program is to build on a lot of the success. We're beginning to have success in HTM-like algorithms as well as the deep algorithms in the DARPA Synapse program. And we're continuing to add more biological detail and just reiterating some of the things that I said earlier. And a major aspect of this is a focus on real applications and entire systems. And I think, as I said earlier, I think there's an opportunity for efficient mapping of specialized hardware. We decided that before we invested in a large program, it would be useful to assess the state of the art in these more biological algorithms. So we're actually going through a 12-month study phase first to look at some of these algorithms and how they apply to certain kinds of benchmarks and data. The goal then is to have a public workshop a year from now that will actually present the results. And my feeling is that if the algorithm results are what we expect, people do what they say they're going to do, I'm more than confident we're going to have enough data to go back to DARPA and say, okay, now we want to do a full-blown cortical processor program. I'm going to skip through some of these slides. They are going to be on the webpage for the conference, but this is just some of the slides that I've used internally to discuss applications for the cortical processor. One of the applications, we talk a lot about system data. I think one of the biggest applications is actually system control. Reaching a point where you're training your system on its data and on its environment rather than programming it. I think it has a tremendous potential in the DoD. So it's not just dealing with sensors, it's also dealing with control. People talk a lot about model-free control. I think that's a real possibility. And then you have all this adaptation going on in the field. I'll skip over that. So anyhow, I'm looking forward to the conference. I think we're going to have a lot of great talks. I'm looking forward to the various discussions we have, both here in this forum as well as privately. I think, sorry, I took too long. Okay.